Hello and Assalamualaikum. So for design for process safety project, which is the consideration of inherent safer design for prevention of major process safety accident, our group has decided to settle on a case study ExxonMobil Torrance Refinery, which is the electrostatic precipitated explosion. This accident happened in Torrance, California on 18 February 2015. In this video, we'll be discussing about the background of the accident, the investigation and analysis, and last but not least, the lesson learned and recommendation. So, without further ado, let's get to it. First, let me introduce the team members. Our group is consists of 4 team members, which includes Muhammad Omar Farouk Muhadzir, Nur Atira Izati Muhammad Azrul Shukri, Kuih Ji, and last but not least, myself, Nur Balkis Muhammad Nasri.
A little bit of introduction. This incident occurs at Torrance Refinery, where it is located at California, United States of America, and this refinery is surrounded by the city of Torrance, as you can see from the figure below. It had a population of 148,000 people in 2015, and it is owned by ExxonMobil Corporation and was constructed on 4 October 1928. Now, let's move on to the detailed process of fluid catalytic cracking. The fluid catalytic cracking units are divided into 2 parts, which are the air side, which is the left side of the picture, and the hydrocarbon side. The regenerator and flow gas system comprise the air side of the FCC, while the distillation column and reactor comprise the hydrocarbon side. Firstly, for the process, the heavy liquid hydrocarbon are fed into the reactor, as you can see from the picture, and they mix with a catalyst. The heavy liquid hydrocarbon is converted into lighter hydrocarbons, vapor, as they travel up to the reactor. As you can see at the top of the reactor, the lighter hydrocarbons vapors are separated from the catalyst. The hydrocarbon vapor will flow from the reactor to the main column, while the catalyst will fall down at the side of the reactor, and it goes back to the slide valve to the regenerator there. And then inside the regenerator, air is added, and the cook of the catalyst will burn off, and the catalyst is then fed back to the reactor through a slide valve, and the cycle is repeated again and again. And then, when the cork is burned off at the catalyst, flue gas occurs. The flue gas will go out from the regenerator and enters a system, as you can see from the picture, compromise many pieces of equipment which removes any remaining catalyst particles present. And you can see from the picture, the last bit of equipment in the flue gas system is called the electrostatic precipitator, or known as ESP, where it removes small catalyst particles using static electricity. Next, moving on to the background of accidents, what were the key events that caused harm? The first event is the spent catalyst light valve cannot isolate the hydrocarbon side and the air side of the FCC unit due to corrosion in the slide valve. Hence, when the hydrocarbon is mixed with air, flammable hydrocarbons occur. The next key event is the use of variants that have been developed in 2012 without verifying the safeguards specified in the past variants were sufficient. First of all, a variance is a management-approved procedure deviation that allows a departure from typical refinery equipment installation requirements. When this variance is used, the steam flow to the reactor had been reduced in order to blind the expander, as we can see from the left picture at the bottom. This leads to the consequence of the steam cannot help to separate the hydrocarbon from flowing back to the air side of the FCC, which eventually become flammable hydrocarbon. Lastly, the ESP remained energized when hydrocarbon entered the flue gas system which contribute to the last key event that caused the explosion. The last event that occurred is the explosion in the ESP. Among the impact from the explosion is fine catalyst dust settled in the community because this refinery is located in the center of the city. Next, from the explosion, there is many injuries occur to the worker and also the property damage to the surrounding units. Also, there is a near miss because the ESP debris impacts scaffolding around the alkylation unit.
The technique we use here is root cause analysis (RCA), which consists of 5-point approach for identifying the underlying cause of incident so that the most effective solution can come out. Why lead to the successive layer of problem? The basic idea of this technique is that each time we ask why, the answer becomes the basis of next why. So by using the RCA, we can dig deeper to find out the root cause of the incident that happened at the ExxonMobil refinery. So first why is why explosion happened. Second, why hydrocarbon fall to the electrostatic precipitator unit. Third, why reactor pressure generated by the steam feed to the reactor was insufficient. 4. Why had no protective catalyst level has been developed. Number 5 is why FCC unit automatically shut down at the initial. To answer first why explosion happened, this is because the slide bath that connecting the electrostatic precipitator and spent catalyst current is erupt and cause the backflow of hydrocarbon into the ESP unit again, which it mixes with the air from the CO boiler and form flammable mixture. Here we identify the highlight. First is the damaged bar in between the ESP and the column. And second, the ignition source is the spark that produced from the charge plate in ESP, which lead to the explosion at the refinery. So you must be curious why hydrocarbon can flow all the way from the regenerator to the ESP unit. Besides erupt bath, the main reason behind the backflow of hydrocarbon is insufficient reactor pressure. Because ExxonMobil management decided to reuse the previous procedure deviation in order to reduce the steam flow rate, which will lower down the pressure present in the reactor. And they're doing this without consulting experienced worker opinion or perform any detailed analysis. Here we lead to another why reactor pressure generated by steam feed to the reactor was insufficient. How is it possible? During the incident at the bath that isolate the air side and the hydrocarbon side failed to maintaining a level of catalyst on top of the bath. So the catalyst barrier that formed in the reactor, we call it plug, which can prevent the reactor process vapor from entering the regenerator. So the highlight that I would like to mention here is the no catalyst barrier has been present. And second, which means it only relying the pressure that generated by 2000 pounds per hour of the steam rate. Number 4, why had no protective catalyst level has been developed? So here, during the FCC unit shutdown, only 2 safeguards has been activated. First is the sufficient steam flow rate, and second is a level of catalyst has to be accumulated on the reactor here. So the problem is the bath is not fully sealed, which caused the low level of catalyst has been present in the reactor, and also it caused the leakage of hydrocarbon that backflow into the FCC unit. As mentioned in previous slide, the 2 only safeguards will be activated when FCC unit shut down in order to put the whole operation into the safe mode. But the basic question is why FCC unit automatically shut down during the incident there? This is because a small amount of catalyst particle has been found out that deposit on the expander brake here, which caused the expander experience high vibration until it reached a high limit, and the control system will automatically begin the emergency shutdown the whole unit. This is the incident flow sheet of the explosion. So during the incident that the expander first experienced high vibration and caused the whole unit shutdown. So the workers are carrying the maintenance works over here. And the 2 only safeguard is the slide bath and the steam flow rate below the reactor. The main purpose of these 2 safeguards is to maintain the sufficient pressure in order to prevent the hydrocarbon backflow from the main column to the ESP unit. But the problem is the slide bar is below, therefore it failed to maintain the level of catalyst barrier in the reactor, and the ExxonMobil management decide to reduce the steam flow rate due to the safety issue of the worker at the expander here. So they decide to reduce the steam flow rate, which caused the pressure also reduced. So due to this reason, the hydrocarbon from the main column have the chance to flow to the reactor and pass by regenerator and separator and go straight to the ESP unit. So during the ESP unit here, it mixes with the air from the boiler and become the flammable material, and the spark that generate in the ESP plate has caused the explosion happen. By using the 5 why approach, we have identified 8 main root causes of the incident. So first, the ExxonMobil are over-relying on the indirect operating parameter and outdated emergency shutdown procedure that has been developed in 2012. So the next is the slide bath could not maintain the catalyst barrier. Reduce the steam flow rate caused pressure deviation that allowed hydrocarbon to enter the flue gas system. Next, the leaking heat exchanger allowed the light hydrocarbon to enter the pressurized main column. Number 6, the ExxonMobil did not completely shut down the FCC unit immediately when it was identified that only one safeguard is worked. And then number 7 is the expander could not be effectively isolated during the worker carry out the maintenance work. Lastly, the ESP unit remained energized although the whole unit has been put into the shutdown mode. Basically, this incident has severely damaged the ESP unit, causing 2 small fires and multiple leaks of flammable liquid hydrofluoric acid. Hydrofluoric acid is a highly toxic chemical that can cause the injury or even cause death. And the explosion debris also punctured a heat exchanger that was out of service. 4 employees has been sent for the emergency. The debris also fell on the building that frequently used by the operator. In terms of community factor, catalyst dust was reported outside of refinery property.
From this incident, we learned that it is essential to identify and define safe operating limits for all modes of operation that measure process condition and parameters that can verify the operation of the process. When a facility relies on process parameter that indirectly provide information on critical process parameter, it leads to the inability to identify an unsafe condition. Secondly, it is critical that the company provide and conduct an MOC to verify and authorize the technical basis and identify any new or affected hazard and its mitigation strategies. If the procedure deviation is safe for future use, the company should verify that the underlying condition, activities, and technical assumptions are still valid. Thirdly, it is essential to schedule and perform maintenance of safety critical equipment so that the equipment is available to perform its safety critical function. The fourth one, it is important to consider all modes of operation when performing PHA. Incident scenario could be possible during non-routine modes of operation that may not have been considered when analyzing process hazard. The fifth one, company should develop operating procedure for all modes of operation, detail safe operating limits, consequence of deviation, and specify action to implement in the event of process deviation. Next, company should implement robust management of change when making changes to the procedure. Similar to PHA, conducting MOC as a multidisciplinary group can assist in identifying hazard in the process. Next, control valve typically should not be used as a block valve because fluid flow through a partially open control valve can cause damage to the valve that can limit its ability to fully seal. And the last one is uncombusted hydrocarbon that are not accompanied by carbon monoxide have the potential to reach FCC ESP unit. So every company need to evaluate their FCC unit to determine whether there are sufficient safeguards to prevent ESP hydrocarbon explosion. For the recommendation, for the first IST strategy, which is substitute, we can change the equipment from ESP to wet gas scrubber. For the minimize, we can use a catalyst that eliminates the need for hydrofluoric acid use. The third one, for the moderate, we can include 2 SCSV in series between the reactor and regenerator, in which the second SCSV functioning as a block valve to accumulate a catalyst barrier. And the last one, simplify, we can install CO analyzer to detect flammable vapor in the flue gas piping, install an emergency ESP bypass, or an emergency grounding system in order to prevent ignition in the ESP. And we can also install an explosion relief panel in order to control the explosion.
As the conclusion of this case study, the incident was indeed preventable. The incident happened because of the process safety management deficiencies. ExxonMobil should have conducted a management of change review, which then will be able to acknowledge the outdated variant of the FCC. Then they should perform an adequate hazard analysis so that they could have identified more effective safeguards against the flow of hydrocarbons. This incident also has been a near miss towards a potential catastrophe. If only the debris has struck the tank, there is a potential of catastrophic release of extremely modified hydrofluoric acid into the neighboring community, which could be very harmful. This kind of management deficiency should be taught and learned by all people so that a similar accident and near miss won't happen in the future. So that's all from our group. Thank you very much.